Hello everyone, today we're going to have a look at the grade 12 physical sciences November 2021 question number 9. So we are given a diagram that is named as a AC generator, and there's also a 25 ohm resistor. Try to just roughly draw it here. So what's important is that before you approach these questions is to identify the machine that we are given. The good thing about this question, of course, is that we are told that it's an AC generator, but we need to be comfortable with what components are making up this machine. So straight up, you can see the big two poles, or rather two magnets. The other magnet is a north pole, the other one is a south pole. And we have a wire here, a coil. We have a resistor of 25 ohms, and then we have these two components which we're going to get into in the first question. And then we have the brushes, and then we have this rod that is sort of connecting these two components. So question number 9.1. We're asked to name the component that distinguishes this generator from a DC generator. So like they mentioned, this is an AC generator, and we're asked to compare what differentiates it from a DC generator. First thing to note, or first thing we should go for when attacking this kind of questions, is what is the difference between an AC and a DC machine, or what is direct current, what is alternating current. So that's alternating current, that's direct current. Direct current simply means that we are not changing direction. So if the current was flowing this way, whatever happens or whatever position the coil is in, we still maintain the same direction of current. But with AC, we have current going this direction, coming back this direction, going this direction. So it is alternating, or it is going in both directions. So it is changing between the positive and a negative current. So what distinguishes this specific generator from a DC generator? So straight up, we should see the components that I said we are going to dive into. Those two are called slip rings. And in a DC generator, we are going to have what we call a split ring. Split, of course, as we see there, those two are split. And if we just put in the same sort of brushes that we see here, we put them beside, and we have conductor here and a conductor here. As this machine is rotating, let's say the current is moving in this direction because of the influence from whatever external circuit we have here. So if the current is going in this direction and we get to a position where the two split rings are at this position, we have the change over. We have the split ring that was on this brush moving over to this other brush. That's if the coil is moving in that direction. So what happens is that the current is still maintained to be going into that brush and coming out of this other brush. But now, when we talk of an AC or an alternating current, it means that there must be some sort of way of not detaching or removing this component, or this split ring from this side and going to the other side. We must keep it there. So what we use is what we call a slip ring. So as we see in this diagram in here, we have these two components. So these components, as this guy rotates, or anti-clockwise, this rotates along with the coil, and there's no point where this slip ring slips from that brush and comes to this brush. And this one also remains here, but it still maintains the rotation. So we don't get a chance to have the current continuously going this direction and splitting over to the next brush and continuously push the current in the same direction. So we end up having current alternating, but we are going to sort of dive into how we get the current to be moving on either direction on the coil. So the major component that makes this an AC generator is the slip ring. The next question, we are asked in which direction will the induced current in the section X, Y be flowing. So, like I said in the previous electrodynamics video, when we're dealing with an AC or with a generator, we use the right hand rule. When we're dealing with a motor, we use the left hand rule. So guess what are we going to use here? Which rule do we use to determine the direction of current? This is a generator, we use the right hand rule. Or as a rule of thumb, we should always understand that when we have a generator, we look for the direction of current. When we have a motor, we look for the direction of the force, because we're putting in voltage and we're trying to get it to move. In the generator, we are having it move and produce electricity. So for the right hand rule in this section, we are told that this generator is moving anti-clockwise. So when it's moving anti-clockwise, in this conductor here, the force is pushing it to go down. On this side, the force is pushing it to go up, so that we have that anti-clockwise direction. So now, what happens to the current? Another thing that we are given in this diagram is the two magnets. The magnetic field moves from the North Pole to the South Pole. So we have the direction of the magnetic field in this way. The force and the magnetic field. So the right hand rule. In the right hand rule, we have the force, we have the direction of the magnetic field, and we are looking for the current. So in here, the force is going down. Alright? But now, do you notice that my finger that is supposed to tell me about the magnetic field direction is pointing in this way? So we need to then flip that finger, and then further flip it to make sure that we maintain the direction of the magnetic field. So the direction of the current is moving this way. I hope you got that. So that's the direction of our current. So we have the current moving from Y to X. It's moving from Y to X. So like I said, make sure you get your rules right. For a motor, the left hand rule, which is the Fleming's left hand rule. And then for generators, we use the Fleming's right hand rule. Now we're going to move into the next question. Question 9.3. I'm going to erase the board and just redraw the graph we're given. Alright, so the first Question number 9.3. It is asking us to define the root mean square potential difference. For a very in-depth explanation of what an RMS is, please look into the video that I'll attach a link in the description below. So straight up, we're going to continue from the knowledge we attained from that video. The RMS is simply the AC voltage component. So in this alternating voltage, the RMS will tell us about, usually RMS is sitting at this point. But like I said, please revise on the previous video. The VRMS tells us about the AC voltage component, such that if you were to take that AC voltage component plug it into a circuit like that. So let's just have that one AC voltage component, or VRMS. VRMS, if we were to take this and plug it to a resistor, we are going to dissipate energy there, or we're going to dissipate power on that resistor. Now, that same value of the AC voltage, if we're to take any equivalent DC value of that, so we change this guy now, we say it's a VDC, so the direct current voltage. We take the same value and we plug it into, or we sort of expose the resistor to the same potential difference. It is going to dissipate the same power. So power is equal to V squared over R. So for the same potential difference, so V of the direct current and the VRMS, if we plug that to the same resistor, we're going to have the same power. So VRMS is the AC voltage component that dissipates the same power as its DC equivalent voltage. Now we're going to have a look at question number 9.4, which is asking us to calculate the RMS current in the circuit. So what I want you to note is that it's easy that now that we're working out the potential difference, to quickly think that the question refers to the RMS voltage. So please reread the question when you're approaching it carefully, that you figure out what RMS are they speaking about, because here we're defining the RMS voltage. So it means here we need to first figure out what's the voltage, the VRMS, or the potential difference RMS. And from that RMS, we then calculate the current that is due to the same RMS voltage. So if you scroll in to the last pages of your question paper, you'll see that the VRMS is calculated as VRMS is equal to Vmax over root 2. And the Vmax here is 100 over root 2. That is going to be that is going to be 70.71 volts. And they are asking us to calculate the RMS. Now, the RMS current, if you also go to those equations, you're going to find that is equal to the voltage RMS over the resistance. So basically, Ohm's law, voltage is equal to current multiplied by resistance. So we have the VRMS is 70.71 and the R is equal to 25 ohms. So the IRMS is equal to 2.883. So for a 25 ohm resistor, so that's 2.83 amps. Now we're going to move into question number 9.5. We are meant to calculate the average power dissipated in the 25 ohm resistor. So just to remember the values you calculated here, VRMS is equal to 70.71 volts, IRMS is equal to 2.83 amps. So they want us to calculate the average power that is dissipated in the 25 ohm resistor. Okay, so power is related to voltage and current through the formula. Power is equal to VRMS times IRMS. Or we should say, so there are three ways to calculate this. Or power, the average power is equal to VRMS squared over resistance. Or we can also say is I squared RMS times resistance. So either way, you can use whatever is in your disposal, but all these formulas should be available in the question paper. So we're going to use this one since we already have those values. So P average is equal to 70.71 multiplied by 2.83, and this should give you this should be 200 watts. So now we're going to move into question number 9.6. Alright, so in 9.6 we are told that the speed of rotation of that the machine we're given is now doubled. So we are rotating the machine anti-clockwise at double the speed that we were sort of using in the previous questions. So they're asking you to draw the new voltage waveform. So this waveform having given the new information that the speed is now 2 times. All right. So before we draw the waveform, I need you to note that, or to just think about the question. So if I was walking slowly and I now walk faster, what will happen? First of all, it means that I'm going to arrive at the destination that I wanted at a much smaller time than what I was going to get up to if I was moving slowly. So we already can tell that this machine is going to cover half the time, because now it's just doubling the rotation. So it's going to cover the point. So if it was rotating this way, so anti-clockwise, this direction, and let's say it started lying like this. So let's say point A, point B. So if it was rotating point A back to point B, and it took, like we saw on the previous graph, it took 0.1 second to come back or to make a full cycle. What is going to happen now that we are saying 2 times the speed? It means we're going to get to this point again faster than the previous time. So we have to have this value here. So we are going to go back to point A at 0.05 seconds. But then they are looking for a time interval. So they want to check if you do the same thing for 0.1 seconds. So if we do this and we get here 0.05 seconds, we still haven't reached the 0.1 second mark. We have to do the saturation again for the second time. So it means we're covering another 0.05 seconds. So we are having 2 cycles within that 0.1 second, because we are now moving faster. So like I said, if a human being is just walking very slowly, they are not going to get where they are going, maybe at a faster time. But if they start picking up the pace, they will get there faster. So when we're speaking of this machine rotating faster, it just means that this point that was here is going to go back to that point at a faster rate than the previous one. All right, so that's the first thing we need to note that will change on our diagram. Another thing is that if when you are turning on a generator, if you could just, I don't know, try to get familiar with it, adjust the generator. It is very crucial to have one of those, especially during load shedding. When you turn on a generator, you put in the force. And if you are just massaging the generator, you're not sort of putting enough force, you're not going to have the generator give out or start acting faster than if you were to really put in the external force, like a higher force than what you're putting at the first moment. So it means that us generating electricity or having the generator run, we need to sort of pull a little bit harder than just being lenient on the generator. What am I getting into here? That the output current or voltage or the electricity that we're going to use is very much proportional to how much we put in at first. So the force that we plugged into the generator is very much dependent or proportional to what we're going to get out as a voltage output. So where am I getting to this? A generator or a coil that, like from the diagram that I'm going to attach here, where we have the coil in a magnetic field. So the coil, and then we had that north pole, and we have that south pole, and we have the coil rotating there. So if we have a coil that is changing or is exposed in a magnetic field and is moving, is in motion, is going to induce current into the conductor. And that is why we are using this left-hand rule and the right-hand rule to sort of figure out the direction of that current. But what we should know is that a conductor that is moving through magnetic field induces an EMF. So this is the formula. An EMF or voltage is equal to number of turns multiplied by the change in flux. So what is flux? Flux is related to the magnetic field. Yeah. So flux is related to the magnetic field, and basically if we didn't have any magnetic field, we were not going to be inducing anything on this coil. So we know that if looking at the previous graph, we have a varying, or we're saying we're rotating this coil around this magnetic field. We have the flux sort of assuming a sine wave, let's say, a sine wave with a certain amplitude and at a certain frequency. A flux, like I said, is very much dependent on the magnetic field that we have here. And as we are rotating the magnetic field, we are cutting, as we are rotating the coil, we are cutting through multiple or certain field lines. And as we are cutting through those field lines, we are inducing, flux. And when we induce current, because the change in flux induces an EMF, and because this generator is connected to a resistor, we'll have current flowing through the circuit. So if I'm making an example here, we have a flux, this flux here, assuming this formula. What we see here is that there's an amplitude, there's a frequency, and there's time. What is frequency speaking about? Frequency we can look at this as omega, where we're talking of the rotational speed. Frequency is how frequent are we crossing a certain mark. So if we're looking at a period, so a sine wave in here and the full period, how frequent or what's the speed that we are getting to a full cycle at. So that speaks to the frequency, or it's very much proportional to the period of basically the frequency is equal to 1 over the period. So we know that if we are moving faster, we're going to influence the frequency. So like I was saying, if now you double this rotational speed, you have the new flux. This was the initial flux. We have the second flux here, which is A sine 2 multiplied by the previous omega times time. So like I said, omega is 2 pi f. So we are multiplying that rotational speed by 2. Why is this important? I'm trying to sort of clarify to you that if you rotate your generator faster, you put in more force, you're going to get more voltage out. But what's the proportion to that? So this 2 that we have here, we'll have to plug in the equation here. So we'll have the flux, and we have to find the derivative of flux. Those who are interested will notice that this 2, when you derive a sine, you get a cos, and then this 2 moves over here, and we end up multiplying the amplitude. So the amplitude changes by a factor of 2, and then we change a sine to a cos. It's probably a minus there. But we have the new EMF, or we have, so that should be positive. So we have the new magnetic field twice that the previous amplitude. So why is this important? So when we double the speed, we also double the peak of our voltage, and we also cover the time that so if we rotate faster, we're going to get to the full cycle at a faster rate than the previous one. So now let's try to redraw what I'm trying to depict here. So if we have 0.1, 0.05, we're going to have our signal going this way. So it's covering the first cycle in 0.5 seconds, if this is time in second, and then it's going up, cutting this guy, and back there in another 0.5 seconds. But what is the peak now? Like I said, we're doubling the cycles that we're covering within the 0.1 second mark, and we're also doubling the peak. So the previous peak was 100 volts, now we're at 200 volts and negative 200 volts. So that's the question number 9.5. Please ask any questions if this confuses you. Thank you for your time.